My name is Jimmy.
Jimmy works for an evil multi-billion-dollar company that pollutes the atmosphere with toxic gases and waste. After reading Martin Rees' This Our Last Century, Jim sees the imperative of a move to sustainable energy. After much research, Jim finds PalCorp. Jim visits PalCorp.
Welcome to PalCorp, Jimmy. The design specifications for this task are as follows: 1 to 3 blades, maximum weight of 500 grams, and a maximum diameter of 500 millimeters. It must self-start at 10 meters per second and must not exceed 3000 revolutions per minute. Finally, it must be designed to have a tip-speed ratio between 3 and 8 at its maximum power output. Our first design choice was to use a 3-blade turbine to maximize energy extraction from the air.
But why do we use 3 blades instead of 2 blades? Wouldn't it save weight and material costs?
Well, 3 blades could be designed to be thinner than 2 blades and hence maintain the ideal planform area while increasing aerodynamic efficiency. PAL also decided to maximize the length of the blades after realizing that the majority of the lift comes from the tip region and that the power was proportional to the swept area. After settling on 3 blades, the next consideration is to determine the optimum tip-speed ratio. Taking into account the fact that the real TSRs are usually higher than the design ones, we chose a TSR of slightly less than 5, which is a typical value for a maximum CP. Having chosen the key aspects of our design, we can start investigating the aerodynamic characteristics of our turbine.
Okay, but start with the basics. How does a turbine actually generate power?
Well, there are 2 component forces acting upon the blade at any one time. Lift, which generates a moment about the axle, and the drag, which opposes motion and in this way reduces the efficiency of the turbine. Ideally, we would maximize the lift-to-drag ratio to optimize the aerodynamic efficiency and the torque produced by the blade. This torque will then drive a power generating device such as a dynamo. There are 3 key design considerations that affect the performance of the individual blades: the shape of the airfoil, such as the camber and the thickness, the span-wise pitch variation, and the span-wise taut length variation. PAL conducted extensive research into different types of airfoils that are used in wind turbines. According to Dr. Giger and Dr. Selig, the SG6040 and SG6043 are appropriate for small turbines. Upon further analysis, we found that the SG6040 is exceptionally efficient and sturdy at the root, and the SG6043 is more aerodynamically efficient for the tip. We therefore decided that we would experiment with a blend of airfoils along the blade. We used the SG6040 for the portion of the blade closer to the root, and the SG6043 for the portion of the blade closer to the tip, with a blended section in between. Because a negligible amount of lift is produced at the root, we decided to use a circular section for structural purposes and to reduce the obstruction to airflow. Utilizing xfoil and airfoils.com, we checked that the research paper by the University of Illinois at Urbana-Champaign was accurate by testing the aerodynamic performance in the relevant flow regimes. We were also able to find the ideal angle of attack for maximum CL, about 10 degrees, which we then used in order to calculate the pitch variation of our blades. There are 2 main equations that can be used to determine this variation: Schmidt's and Betz. Both equations consider the effect of the rotation of the blade on the incident angle of the airflow. However, the Schmidt's equation also considers the added effect of the rotation of the wake of the airflow due to the spinning rotors. Because of its more sophisticated approach, we use the Schmidt's equation to define the pitching of the blade along the radius, such that the angle of attack remains at the optimal value with respect to the incident flow velocity. Finally, to design an efficient airfoil, we need to optimize the taut length. Our objective in deciding upon the taut length variation of the blade was to maximize the lift-to-drag ratio and maintain a constant circulation along its span. We had 3 different options: the inverse X relationship, the Betz factor, or the Schmidt's factor. Again, only the Schmidt's equation considers the rotational flow of the wake, and Dr. Patel, in his book Wind and Solar Power Systems, Design, Analysis and Operation, agreed that Schmidt's was a much more accurate and realistic equation to derive an ideal airfoil. For these reasons, we decided to use the Schmidt's equation.
Okay, so you've made sure the airfoil is all optimized, but how do you know it won't just break apart?
Well, that's the next part of the design process. We have to ensure that what we have come up with so far is within material limits we have to work with. As with most structures, we can break down our internal forces into those acting in plane with the blade and those acting perpendicular to it. First, we looked at the bending stresses that occur due to the force imparted on the blade by the oncoming wind and the inertial forces acting against the rotation. By applying the known conditions, such as the free stream air velocity and the predicted angular velocity, we can model the response to such forces using these equations. Luckily, we found that bending moment experienced by this design are within material limits, with a large safety factor of 44%. The other structural consideration is the centrifugal force that acts on the cross-sectional area of the blade due to the rotational inertia. By integrating the mass of the blade along its span, the tensile forces due to the spinning mass could be calculated. The rotational inertia is at its maximum at the root, and thus it was important to ensure a suitable cross-sectional area. After including a safety factor, we chose a diameter of 15mm. Okay Jim, enough about the blade, let me tell you about how we went from concept through prototype.
Oh, but I have so many questions.
Calm down Jimmy, you can ask them at the end of my pitch. Once we had our specifications sorted, we used the computer-aided design program called Creo to realize our design. Okay, let's have a look at the hub, upon which we will mount the aerodynamic part of the turbine. We designed the hub in a hexagonal shape to improve traction. The blades were created using multiple airfoil sections, which were blended together using the software. Finally, we modeled the nose cone in an ogive shape, much like those seen in typical everyday windmills. This is done in order to minimize the interference effect on the root of the blade and reduce drag. The drawings we created in Creo were then used as a reference throughout the manufacturing process. Let's move on to the manufacturing stage. The aluminium hub was milled manually using a variety of precision tools. We then used the rapid prototyping machine to manufacture our blades and nose cone in multiple parts using our Creo models. The different segments of the blade were glued onto the nose cone and the turbine were sanded. Following this, we applied a layer of lacquer to improve the smoothness and hence aerodynamics of the blade before conducting another round of sanding. Including the hub, the weight of the turbine was found to be about 150 grams.
Wow, it's really starting to take shape. So how did it perform?
Well, taking into consideration that we took a novel approach to designing the blades, we were cautious in our expectations. Unfortunately, the testing of our initial design was not successful, as the wind turbine did not self-start at 10 meters per second or even at higher wind speeds.
So what went wrong?
We observed that two of the blades were bending slightly forwards and the pitch of the blades were altered due to the airflow. Furthermore, the whole of the hub was not centered. We decided to reprint the blades to fix these manufacturing defects and rerun the test. However, testing the newly printed wind turbines had the same results as our first test. This clearly indicated that our design was flawed. We hypothesized that the thin flexible wind tips were the cause for this failure. We decided to cut the blades to almost half the length and hence remove these thin tips. If the turbines were to work effectively now, it would prove our hypothesis. Our test showed that despite it again failing to self-start, it eventually reached a maximum RPM of 2600 after being given a small push. This smaller wind turbine seemed to have a considerably better performance than our first turbine, allowing us to understand the limitations of our design. The wind turbine was operated at 10 and 12 meters per second. With the changes made to the wind turbine by clipping the wind tips, our expected TSR dropped to 2.6. Our modified wind turbines had a TSR that deviated by less than 2% from the expected values at all wind speeds. The strong correlation between expected and experimental TSRs suggests that the wind profile was accurate and that the performance results could be predicted using our design parameters. The turbine produced a maximum output of 0.114 at a wind speed of 12 meters per second. The power generated by this wind turbine is enough to light up a bulb.
Wow, that's moderately impressive. But what were the flaws? What can you guys do to come up with a better turbine and save the world?
The final test proved the hypothesis that the main issue was that our blades were too thin, especially near the tips. This resulted in a lack of stiffness, causing the tips to bend backwards and adopt a dish shape. Hence, instead of generating the majority of the lift, large amounts of drag were produced. When predicting the structural behavior of the blades, we only considered the failure modes that would arise due to bending moment, without investigating the flexural stiffness and the effects of bending on the aerodynamics of our design. In the same vein, the total planform area for our wind turbine was not as large as required for optimal generation of lift. We realized that the formula for the ideal planform area was something that we had failed to include in our design considerations. Finally, many of the shortcomings of the turbine were due to the choice to design the blade to operate optimally while already rotating at its maximum TSR in 10 meters per second winds. This meant that we did not consider the self-start requirements sufficiently. To prevent this, more analysis could have been done in suboptimal operation conditions, particularly from when the blades were at rest and accelerating to the maximum TSR.
So what are you guys going to do about it? Are you just going to scrap the entire project?
Not at all, Jim. Testing and redesign is an integral part of the evolution of a product, and we would definitely look at improving our design in the following ways. we would incorporate the planform area equation and have a thicker aerofoil closer to the tips. Also, we would consider reducing the size of the nose cone and hence increase the length of the blade to better improve the performance factor. With dwindling natural resources and a rise in demand for clean electricity, it has never been more necessary to create an efficient, sustainable source of power. Hence, PAL will continue pumping its resources into the research and development of a more efficient wind turbine using hybrid blades.